Hi everyone. Thanks for coming to my presentation. My name is Wesley Black. I'm going to be talking about my project, which was fuzzing web applications without instrumentation via response times. So before we start talking about the project, I just want to give a brief background on what fuzzing is in general. So fuzzing is a software testing technique where a program gets fed a large number of automatically generated inputs in order to find bugs, to find crashes, or to find some unexpected behaviors. And if the program crashes, if it hangs, if it has some kind of error that occurs, the input gets flagged and gets output for someone to investigate a bit further. And since the whoever's investigating will have the input along with whatever else the fuzzer outputs, it makes it a lot easier to fix these bugs. So there are three broad categories of fuzzers. You have black box fuzzers that have absolutely no knowledge of the internal states of a program. You have white box fuzzers that know everything about the program. And in between you have gray box fuzzers that have no access to source code, but it does collect some feedback from the program as it's running, typically how many lines of code were executed during a run, so it can use that to guide its mutation. Now I want to talk about what is the motivation for this project. Well, right now, current web application fuzzers kind of have a gap. You have brute force black box fuzzers that have no guidance at all. They're just completely brute force. They get a word list and they go through that word list to see what it can find. And because of that, it has poor coverage. And if you have poor coverage, you're not going to find a lot of bugs because the more code you cover, the more bugs you find. Now, on the other side, you do have instrumented gray box fuzzers, such as Fuzz, WebFuzz, Tropos. But these fuzzers require instrumentation, so the user has to go through to a PHP interpreter, set that up to be instrumented, and report coverage back to these fuzzers. And because of that, these ones only work with specific languages, and in this case, they only work with PHP. So what this project aims to do is to create a fuzzer that's kind of in between these two types of fuzzers. Something that is still capable of receiving guidance from the program and cover a bit more code than a brute force black box fuzzer, but one that doesn't require to any kind of complex setup. It doesn't require any instrumentation and can work with a wider variety of languages. To that end, I decided that timing might be a good way to guide coverage. Now, using timing would be possible because code paths that do more work take more time to execute. And you can use timing to kind of figure out, was a new code path reached? Because if it was, it should take a little bit longer. And this has actually been used in the past in a paper, Remote Timing Attacks Are Practical, by Brumley and Bona, and what they demonstrated was that timing differences being recorded can actually leak secret key information. And so spending more time waiting for a response hopefully means that it should reach more code and is executing more code. And since we're using response timings as a way to guide mutations, it doesn't require any instrumentation at all. It should just be, you have the web application, you have the fuzzer runs, you don't need to do anything special with the web application for it to report back. So what's the threat model for this? Well, I'm assuming that the attacker can control requests, can send whatever requests they want with any parameters that they want at the website, that the website will only accept the correct parameters, correctly formatted HTTP requests, and that a specific sequence of inputs, a specific parameter set, will lead to the website crashing. Now, there are four primary challenges that were faced when creating a fuzzer that uses timing as guidance. The four main challenges faced were fuzzing HTTP requests in the first place. Because when you're fuzzing HTTP requests, you want to make sure that these requests are valid. The second one was detecting crashes, because since have no knowledge on the program, we can't even see the program, we can only see the responses. We don't know if it's crashed or not. The third challenge was actually classifying timings, because if you get times that are very similar, you don't actually know, well, did one input actually lead to a new code path? Is it the same code path, or is it a different code path that does the same amount of work? And the final one is slightly related to the third challenge, but the final one is the timing variation. You get slight variations in the amount of time it takes to get a response, and being able to figure out, well, was this a result of just a random delay or not, can get pretty difficult. I'll be going more into these challenges in the next few slides, so stay tuned. So going back to the first challenge faced, fuzzing HTTP requests, the fuzzer needs to actually ensure that all of the HTTP requests are actually valid, because if they're not valid, they get rejected. If they're malformed or invalid, just rejected. Doesn't reach the application code, it's just rejected, and it gives us absolutely nothing useful about the actual program. The response times aren't correct because since it was rejected, it's not really going into the code that far. So to get around that, you actually have to set up which parameters are being sent. So the user has to say, okay, this is the group of parameters that are being fuzzed. This is the one that needs to be fuzzed. It takes a little bit more work than automatically fuzzing, but it ensures that every request is valid, that it's going to reach the application, and it's not going to be rejected, and we will get useful responses. The second challenge, knowing what the server is doing. If you can't see what the server's state is, you only can see how long the response took. How can you figure out whether you crashed or not? I'll give you a few seconds to think about that one. So, with this fuzzer, what we do is we assume that any timeouts are going to be a crash. We actually wait about 10 seconds after sending a request. If we don't receive a response back in those 10 seconds, we assume that the server has crashed, and as such, whatever input, whatever cookies were sent to the server get output to a file for the user to review. Otherwise, if it does get a response back, but it happens to be an 500 error, which signifies a server-side error, the fuzzer will also output the input and the cookies, because it assumes that if it's a 500 error, something's gone wrong with the server, and the developer would like to know what has gone wrong. So on to the third challenge. What do the timings mean when you're trying to classify the timings? Let's look at just a small example. What if you have two completely different inputs that both go down two completely different code paths, but these two code paths happen to do the same amount of work, taking the same amount of time to execute. So when you time the response, both of these inputs take the exact same amount of time. So how can you figure out when the timing is interesting and should be saved? It's actually the challenge faced by this fuzzer. And so what this fuzzer does is it just treats any input that meets the timing threshold, gets saved as a new code path to be explored further later on. Now, what is the timing threshold? The timing threshold is the time it took the seed to execute multiplied by a timing sensitivity, typically 1.01, 1.2, just slightly higher than the seed value. So, the final challenge, timing variation. What are some factors that affects the response timing? I'm going to give you a few seconds to think about that question, and if you look ahead on the slide, you'll probably already know, but take a few seconds to try and guess. So some of the factors that can affect response time, you have the scheduler deciding not to schedule the program. You can have random network delays that cause the responses to take a little longer to get back. Or you can have some CPU load causing it to take a little longer. And that can all cause the same input to take a varying amount of time. And so to solve this, what the fuzzer does is it actually sends multiple requests. And it compares the timings of those 3 requests. If one response takes way longer than the other 2 requests, and it tries sending the request again to get the time again. And then once it gets all the timing requests done, all the responses timed, everything done, it then averages them out to try and get a good number to see, alright, how long did it actually take? Now, the timing sensitivity threshold is also here, just like last time. It just filters out some of the responses by making sure that there's some improvement over what the seed actually was. So if it's only a few microseconds higher than the seed, it doesn't get saved. So now we move on to the design of the fuzzer. A couple core components, some of them pretty normal for fuzzers and some of them pretty unique just to web application fuzzers. So the core components for the fuzzer, first it has to generate a valid HTTP request, which, as we saw from the challenges, we already have that handled. Then it has to time the HTTP response and has to figure out, okay, how long did this HTTP response take? Is this input worth saving to mutate off of in the future? Then it has to interpret the HTTP response. It has to say, okay, did we receive any cookies? And if it received cookies and we're saving this input, then we have to save that cookie along with the input so it can be sent alongside the input in the future. It also has to figure out, alright, did it have a 500 error code response? Did we even receive an HTTP response before we timed out? And then if it didn't receive a response, if it got a 500 error, then it has to report it. So how does it generate a valid HTTP request? Well, it starts off with a seed that it generates with a valid request from the user generation, and it sends that to get a timing, brings it back, and what it does next is it takes that input and changes a single byte in that input. It sends it out, waits for the timing response to get back. And that way, it can make sure that each request remains valid. It's not changing the entire request, it's just changing the parameters in the request to make sure everything still remains valid. Then it has to time the HTTP response. Time's measured in 2 spots. It's timed right before sending the request and right after receiving the request to make sure that as little extra stuff is in between the 2 as possible. Now, since it sends 3 requests, it has to do that 3 different times, and as mentioned prior in the challenges, it does have to check if these requests and the timing meet the threshold of the being higher than the seed by a certain amount. And if it does, terrific, it gets saved into the seed pool, gets mutated off of in the future. If not, it just gets discarded and the fuzzer gets to try again. So then the fuzzer has to handle HTTP responses. Has to check the responses for error codes, of course, and checks, well, was a 500 error received? If so, there's a server issue. Report out to the user, write the input to the log, report the cookies, and go ahead and end. Otherwise, if there's no error code, it checks, did it time out? If it timed out, then does the same exact thing, reports it out for the developer to look at the input later and see what went wrong with the website. Finally, has to handle any cookies that are received as part of the response. As mentioned previously, if there are cookies that are received with the response and the input gets saved, then those cookies also get saved. So in the future, and when that input is mutated off of, that cookie that was received gets sent out back alongside the new input. Now we move on to the more fun part of the project. Past the design, past it actually being programmed and being set up. Now we move into actually running it, testing it, and checking, can timing be used to guide mutations? So, to do this, we actually ran the fuzzer 10 runs per time delay. We had 4 different time delays. We had 1000 microseconds, 150 microseconds, 100 microseconds, and 90 microseconds. And each run we did 10 runs. Each run we ran for either 12 hours at max or until it found a crash in the web application. And so we had 3 different questions that we wanted to answer. 1. Can the fuzzer detect new code paths more than 75% of the time? 2. Does changing the time sensitivity affect the number of test cases required? And 3. Does the timing guided fuzzer actually outperform a random black box fuzzer? So in order to evaluate the fuzzer, I needed to create a application that was controlled by me, that could see what the fuzzer was doing to the application, and where I could control the code paths in the application. So I created a web application written in Python using the Flask library. This let me set up some code paths where I could simulate code path delays with those 100 microseconds, 150 microseconds, 90 microseconds, 1000 microseconds using sleep calls. That way it would prevent any kind of optimizations, any kind of cache optimizations, processor optimizations at all, and it would just sleep. I would also created in the web application a deep path that would trigger a crash once it was reached. So, for the results, can the fuzzer detect new code paths more than 75% of the time? The answer is yes, when it's either 100 microseconds or above that the code path takes. As you can see from the chart here, the number of successes for 1000 microseconds was 10 successes out of 10 runs. 100 microseconds, also 10 successes out of 10 runs. 90 microseconds did not. 90 microseconds only had 7 successful runs out of 3. Now, why did 3 runs of the 90 microseconds not succeed? Well, it was because the 90 microseconds, they sometimes just did not find the right code path. And they would just continue to run, and it would keep finding non-new code paths that happened to take slightly longer than the actual code paths, and it would save those over the regular code paths. And then it would keep having random delays that would also push it over the save threshold. So it would just keep saving non-new code paths over and over and over again, wasting mutations. So, next question. Does changing the timing sensitivity actually affect the number of test cases required to find the crash-causing case? So for this test, I ran 1000 microsecond delay with 4 different timing sensitivities. Timing sensitivity of 1.5, 1.25, 1.1, and 1.01. So, as you can see by this table here, the timing sensitivities 1.5, 1.25, 1.1 had a lot fewer test cases than 1.01. This was because at 1.5, 1.25, 1.1, with 1000 microsecond delay, it was very obvious to tell when a new code path was taken. And so, with higher timing sensitivities, it is far less likely to detect non-new code paths, non-code paths, just random variances as new code paths. So it doesn't get lost, it keeps on track. But at 1.01, any random timing noise would meet the bar of the threshold. And so the seed pool would just get completely filled with false positives. Now for the final question. Does the timing guided fuzzer outperform a random black box fuzzer? Now for this test, the random black box fuzzer is very similar to the timing guided fuzzer that was designed and implemented here. But what the black box fuzzer does is instead of taking the time, instead of recording it, it just goes ahead, generates some random inputs, and sends that out. It doesn't care what the results are, only cares as far as cares to see whether it crashed or timed out. Now what I saw was that the timing guided fuzzer did require far fewer test cases than the random fuzzer, which you can see here. The timing guided was about 3,000 test cases versus the random fuzzer's nearly 500,000 test cases to find the crash case. Now something interesting you might note about this table is that the timing guided test per seconds is actually a bit faster than the random black box fuzzer. Now when I looked at the web application and the fuzzer to see what was going on, I actually found that the timing guided fuzzer, when it was taking time to actually save the seed and going through and waiting slight delays with actually hitting new code paths, the web server was getting a little bit of extra time to actually handle all these requests. But with the random black box fuzzer, since it just kept shooting off requests, the server had a slight delay from handling these requests that it actually affected how fast that the random fuzzer would actually receive a response and could check whether it crashed or not, causing it to run just a bit slower than the timing guided fuzzer. So now we're going to take a look at some observations I saw as I was testing out the fuzzer and evaluating its performance. So here's my question. How do you think that the test per second will change as the delay changes? I'll give you a few seconds to think about that. So if you look at the table, you'll see that as the code path delay decreased, the test cases per second tended to increase. At the same time though, when you look at 90 microseconds, the test case per second actually decreased again. So you might be wondering, why is that? Well, at higher code path delays, for example the 1000 microseconds, the fuzzer, once it starts finding new code paths that take that 1000 microsecond delay, has to wait those full 1000 microseconds to actually get a response back. And the further it gets into the code with even more delays, you can start getting into a couple thousand microsecond delay, causing the fuzzer, every single input with the actually reaching into the code path taking a couple thousand microseconds to get back, which actually causes quite a bit of a delay. So decreasing the delay increased the number of tests that could be done because it was getting responses back faster. But at 90 microseconds, what was interesting was that it actually decreased again. Now, this was because there were a lot more false positives occurring, and the fuzzer had to go through and save all of these false positives in the seed pool, taking up a lot of extra time as it was saving. So before we start this slide, I want you to take a moment and think, could there be variance between the runs? And if there were, how bad could it be? And what could be causing these variances? Give you a few seconds to think about that. So the answer was yes, there's some variance between runs. And in this table here, you can see the standard deviation in the number of test cases. Now, what causes such a big number of deviation in these test cases? For example, 1000 microseconds, you see that there is deviation about 11,000. This is actually because if there were early false positives being saved in the seed pool, it can actually delay it by quite a lot. A majority of the its 1000 microsecond delays ended up being pretty quick, within a few thousand. But there were a few runs where a false positive was saved early, and that caused the program fuzzer to take around 30,000 test cases to actually find the actual crash case. And you can see that from 90 microseconds that there was a massive difference in test cases, 116,000. This is because in some runs, the fuzzer would find the crash case pretty quickly. The false positives wouldn't overwhelm it. But in other runs, it would find a lot of false positives, and it would take a lot more time for it to actually narrow down the actual correct code paths and get rid of and overwrite the false positives. Now, from the previous slide, you might be wondering, if there's still false positives and timing sensitivity is supposed to filter out these false positives, how do I know what to set the timing sensitivity to? Well, this is where knowledge of the application can come in a bit handy. If you know your code paths might be taking a bit more time to run through, you can set the timing sensitivity a bit higher. And if you can time out your application, you can figure out how long these code paths are taking. It becomes a lot easier to figure out, okay, well, my time sensitivity should be X because the code paths are going to be taking Y amount of time. But in general, if you're not sure, there is a trade-off between setting a low sensitivity and high sensitivity. At a low sensitivity, you're going to have a lot more test cases going through because you're going to have a lot more noise and it's going to affect your fuzzer and you get a lot of false positives, but you will probably hit a lot more code paths. But if you set it to a high sensitivity, it filters out the false positives, but it can also filter out real paths that might take a short amount of time, do a small amount of work, and so the fuzzer can miss those code paths. Now, from the previous slide, you might be wondering, if there's still false positives and timing sensitivity is supposed to filter out these false positives, how do I know what to set the timing sensitivity to? Well, this is where knowledge of the application can come in a bit handy. If you know your code paths might be taking a bit more time to run through, you can set the timing sensitivity a bit higher. And if you can time out your application, you can figure out how long these code paths are taking. It becomes a lot easier to figure out, okay, well, my time sensitivity should be X because the code paths are going to be taking Y amount of time. But in general, if you're not sure, there is a trade-off between setting a low sensitivity and high sensitivity. At a low sensitivity, you're going to have a lot more test cases going through because you're going to have a lot more noise and it's going to affect your fuzzer and you get a lot of false positives, but you will probably hit a lot more code paths. But if you set it to a high sensitivity, it filters out the false positives, but it can also filter out real paths that might take a short amount of time, do a small amount of work, and so the fuzzer can miss those code paths. So this fuzzer tends to send a lot of requests in a short period of time, and so I'm going to give you a few seconds to think. What does a normal server do when it starts receiving a lot of requests from one client in a short amount of time? And if you said the server is going to assume that it's under attack and block the client, you'd probably be correct. If you were to use a fuzzer against a real server, you'd want to introduce some delays in between the requests so it's not overwhelming the server and not getting blocked. Or you'd want to change the server to not block someone who's sending a lot of requests in a short amount of time. Now, another issue is that a lot of applications tend to have code paths that don't do a lot of work. For example, setting a single variable or adding two numbers together, something very small. The fuzzer here cannot easily detect that kind of stuff because it's very short, very quick, and with the random network delays, it'll get lost in those delays. If you were to use a fuzzer against a real server, you'd want to introduce some delays in between the requests so it's not overwhelming the server and not getting blocked. Or you'd want to change the server to not block someone who's sending a lot of requests in a short amount of time. Now, another issue is that a lot of applications tend to have code paths that don't do a lot of work. For example, setting a single variable or adding two numbers together, something very small. The fuzzer here cannot easily detect that kind of stuff because it's very short, very quick, and with the random network delays, it'll get lost in those delays. So, in conclusion, what does this work show? What happened with this project? Well, this project has shown that this fuzzer can find crash-causing inputs and new code paths when the delays are more than 100 microseconds or equal to 100 microseconds. It also showed that timing-guided fuzzing is possible, and that it requires no instrumentation of the target web application, and that it can indeed outperform a black box fuzzer. And my name is Wesley Black. Thank you for coming to my presentation on fuzzing web applications without instrumentation via response times. I hope you enjoyed it, and make sure you leave a like and comment and go ahead and subscribe.